Greetings of the day to all of you. In today's lecture, we will discuss the active power and reactive power flow over a long high voltage AC transmission line, and we will try to understand certain conditions for the flow of active power or for the transfer of active power over the line, the transfer of reactive power over the line, then reactive power demand and reactive power loss, active power loss, and all that. Let us take again two machine model of a transmission system. I will write here power flow over an AC transmission line. Okay, the two machine model of the system is like this. The line reactance is X. The line impedance is predominantly reactive or inductive. That's why I'm writing X. I'm ignoring R for the time being. The transmission line resistance I'm ignoring for the time being. The current flowing is I. This is the sending end voltage. Let us say it is Vs at an angle of delta, where delta is the power angle or transmission angle. Vs is the sending end voltage. The voltage at the receiving end is Vr. Let us take it as reference. Vr at an angle of 0 degree. So this is the model. The power which is generated at the sending end is apparent power is Ss is equal to Ps plus jQs. It has active power component and it has a reactive power component. The power at the receiving end, apparent power at receiving end is Sr equal to active power component Pr plus J times reactive power component Qr. Right? So now I will write here power at receiving end. How much power will be there at the receiving end? That is Sr, apparent power, which is equal to Pr plus jQr. In terms of voltages and currents, that is given by receiving end voltage Vr multiplied by complex conjugate of the current I star. I star means complex conjugate of the current. So Sr is also given as Vr, and if you study, if you see the current over this transmission line is voltage at sending end minus voltage at receiving end divided by the line reactance. So it is Vs minus Vr divided by Jx complex conjugate. Right? Now we already know this Vr is equal to Vr at an angle of 0 degree. That is Vr cos 0 degrees plus jVr sin 0. Now cos 0 is 1, sin 0 is 0. So Vr into 1 is Vr. So it is Vr itself. Similarly, voltage at sending end Vs is Vs at an angle of delta, as you can see. That is Vs times cos delta plus j sin delta. That is equal to Vs cos delta plus jVs sin delta. So we will substitute it in this equation. So therefore, apparent power at receiving end is equal to Vr times Vs. Vs is Vs cos delta plus jVs sin delta. I will write here Vs cos delta plus jVs sin delta minus Vr. Vr is Vr itself, because it is at an angle of 0 degree. So it is Vr divided by Jx conjugate. Right. So this can be written as, Sr can be written as, Sr is equal to Vr times, if I write Vs cos delta minus Vr, right? And I then write this imaginary term. I have taken the real terms together. Vs cos delta is real part, Vr is also a real term, and then this is the imaginary term. That is j plus j times Vs sine delta whole divided by Jx conjugate. So therefore SR will be equal to, if I take this real part first, it is VR times, real part is J Vs sine delta by Jx, because this x, this term is divided to be divided by Jx, this term is also to be divided by Jx, plus then we have VR times this. First I have multiplied this in this divided by this, I got this, and then I will multiply this term with this term. This term is Vs cos delta minus VR by Jx. Okay, this is complex conjugate, of course. Okay, so it is like this. So or let me put the whole thing within a bracket. So it is complex conjugate. So SR therefore from this equation is equal to, now from here you can see J and J cancel, so it is Vs VR by X sine delta, right, plus Vs into VR is Vs VR cos delta minus VR into VR is VR square by Jx conjugate. So if I remove this star, complex conjugate, so then this SR will be equal to Vs VR by X sine delta. Then this star, if I remove this star, then this plus will become minus Vs VR cos delta minus VR square, and this will also become minus. It was plus Jx, it will become minus Jx, right, after removing this complex conjugate, this star. So this will become SR is equal to Vs VR by X sine delta. Now you can see this is minus J, this becomes plus, but when this J goes up, okay, let me first of all write Vs, I will do it step by step, Vs VR cos delta minus VR square by Jx. This minus and minus cancel, it becomes plus. Now therefore SR will be equal to Vs VR by X sine delta. This J, when it goes up, it becomes minus J times Vs, is it minus J or plus J? It should be plus J. Yeah, it should be plus J. Here it should be minus J. This is yeah, plus, and this is minus J. And when this minus J goes up, it becomes plus J. Plus J Vs VR cos delta minus VR square by X. Okay. So therefore this is SR. This is the mathematical expression for SR. Now this SR is apparent power. It has a real power term and it has an imaginary power term. So real power, reactive power is imaginary term. Real power is given by this Vs VR by X sine delta, and reactive power is given by this this term, imaginary term, that is Vs VR cos delta minus VR square by X. So this is the real power at the receiving end, and this is the reactive power at the receiving end, and total apparent power at the receiving end is this. In a similar way, if you find the expression for this real power at the sending end, Ps, that will have same expression, that is equal to Vs VR by X sine delta, and a reactive power at the sending end will be Vs square minus Vs Vr cos delta by x. You can derive same way this real power and reactive power at the sending end. Okay, so these are some very important equations. With the help of these equations, we have found what is the apparent power at the receiving end, and then we have the real power component of this and the reactive power component of this. Similarly, the real power at the sending end is this, and reactive power at the sending end is this. Let us now consider different cases. Okay, we'll consider case A. So before we consider case A, let me try to draw the phasor diagram. Phasor diagram will look like this. Phasor diagram of this system will be like this. If you take receiving end voltage as a reference, VR, let us say current is lagging behind the voltage by certain phase angle phi. So there will be reactive voltage drop JIX, and then this will be the sending end voltage VS. And the angle between Vs and Vr is delta, which is also called power angle, or which is also called transmission angle. So this is it. So this is the phasor diagram. Now let us consider two different cases. First of all, we will consider case A. In case A, let us assume delta B equal to 0 degree. So when delta is equal to 0 degree, you can see from these equations, sine delta is sine 0 in both these equations, that is 0. So when delta is equal to 0 degree, that means when sending end voltage and receiving end voltage are in phase, there is no phase angle or phase difference between the two. Transmission angle or power angle is 0. Then there will be no active power transmission at the receiving end. There will be no active power transmission at the sending end. So therefore, sending end active power will be equal to receiving end active power, and it will be equal to 0. Absolutely 0. Okay. What about reactive powers at sending end and receiving end? Reactive power at sending end, you can see from this equation, put delta equal to 0, so cos 0 is 1, so it will be Vs square minus Vs Vr, because cos delta is cos 0 is 1, so divided by x. Or we can say Qs is equal to, if you take Vs common, so you will get 1 minus, Vs minus Vr by x, right? So this is the reactive power at the sending end for delta equal to 0 degree. What about reactive power at the receiving end? In a similar way, reactive power at the receiving end is given by this equation here. Again, it is cos delta, and this is minus, how much is this? This is minus Vr square. Okay, so you put delta equal to 0 degree, so cos 0 is 1, so it will be Vs Vr minus Vr square by x. Or we can say a reactive power at the receiving end, take Vr common, so it will be Vr times Vs minus Vr by x. So therefore, for delta equal to 0 degree, active power at both sending end and receiving end is 0. There is no transfer of active power either from sending end to receiving end or from receiving end to sending end. No active power can flow for delta equal to 0 degree. Okay, which is a hypothetical situation. But there will be reactive power at both receiving end as well as sending end. Reactive power at receiving end is given by this equation, and reactive power, this is reactive power at sending end, and reactive power at receiving end will be given by this equation. Fine. Now, will reactive power flow from sending end to receiving end, or it will flow from receiving end to sending end? That depends upon the voltage. For example, Qs, I will write again, Qs is equal to Vs times Vs minus Vr by x. Now, if sending end voltage is greater than receiving end voltage, right? So this term will be positive. This term will also be positive. That means both Qs and Qr will be positive. What does that mean? That means, so let me write here, for sending end voltage to be greater than receiving end voltage, Vs greater than Vr, Qs and QR or positive. And positive means there is a lagging power factor. I mean, the positive reactive power means inductive reactive power. It means from circuit theory we know that positive reactive power means inductive reactive power. There are two types of reactive powers, inductive reactive power and capacitive reactive power. And whenever there is inductive reactive power, that means there will be lagging power factor operation, which means reactive power is absorbed. Reactive power is absorbed. There will be reactive power generated at sending end, and there will be some reactive power generated at receiving end, and these reactive powers are absorbed by the load. Your load itself is reactive in nature. It's a lagging power factor load, and it demands reactive power. So therefore there will be reactive power generated at sending end as well as at receiving end, and this reactive power will be absorbed by the load. Okay, so when there is a positive reactive power flow over the transmission line, it means the receiving end voltage will decrease. The receiving end voltage will be less than sending end voltage, so receiving end voltage drops. So there will be a drop in the receiving end voltage. So this we can explain, I can explain with the help of a simple phasor diagram. Let us suppose this is receiving end voltage, take it as a reference, and let us consider this situation, reactive power positive. Positive reactive power means current is lagging behind the voltage by 90 degrees. That means your load is purely inductive in nature. I mean, your load demands reactive power, it's absorbing reactive power. And from the two machine model, you know, this is sending end voltage and this is receiving end voltage, and reactance is X. From this, what will be the voltage drop? If this is the receiving end voltage and there is current I, which is the reactive current flowing through the transmission line, this current I will result in I into X voltage drop, and I into X voltage drop will be at 90 degrees with respect to I. So if this is your Ix will be like this, because in an inductive circuit current lags behind the voltage. So this is your voltage drop. Voltage drop leads the current, or current lags the voltage. So therefore your voltage drop Jix will be, Ji into X will be like this. So therefore what is sending end voltage? Your sending end voltage is this receiving end voltage plus this Jix drop. So therefore this arrow will be your sending end voltage, Vs. Okay, so therefore you can very clearly see that sending end voltage for positive reactive power, when you know, positive reactive power is flowing over the line, that means when load demands a lagging power factor, load is a lagging power factor load, then the sending end voltage will be greater than receiving end voltage, or in other words, the receiving end voltage will be less than sending end voltage. In fact, receiving end voltage will be sending end voltage minus this reactive voltage drop. Higher is the reactive power demanded by the load, larger will be this drop component and smaller will be the receiving end voltage. So therefore receiving end voltage will be always less than sending end voltage for such a situation. Okay, so this is one point. Another very important point is, if reverse is true, that means for receiving end voltage to be greater than sending voltage, I mean if receiving end voltage is greater than sending end voltage, or sending end voltage is less than receiving end voltage, in that case what will happen? From those equations we can find that sending end reactive power and receiving end reactive power are both negative. They are both negative. And what does negative reactive power mean? Negative reactive power means that reactive power is not absorbed by the load, but reactive power is generated and it's injected into the transmission system. This means reactive power is generated. Reactive power is not absorbed. Reactive power is generated and it is injected into the transmission line. So therefore load is not absorbing the reactive power, but there are certain components which are generating the reactive power. So reactive power, that's why the reactive power is negative. So negative reactive power means it is a capacitive reactive power. Capacitive reactive power. Just like positive reactive power means reactive power being absorbed, which means inductive reactive power. Negative reactive power means reactive power being generated, which means capacitive reactive power, which means leading power factor operation. Your transmission line is operating at leading power factor. And in case of leading power factor, you will see that receiving end voltage will increase. Receiving end voltage increases. For lagging reactive power, just few moments back, you have seen that receiving end voltage is less than sending end voltage. It drops because of this reactive power voltage drop. But for capacitive, when reactive powers are negative, that means capacitive reactive power, leading power factor operation, receiving end voltage does not drop, it increases. It is higher than sending end voltage. That we can explain with the help of, we can understand with the help of this Phasor diagram again. So this is our Phasor diagram. For example, again, this is receiving end voltage Vs. Now current is leading the voltage. It is not lagging. In the previous case, current was lagging the voltage. In this case, current is leading the voltage. So it is a capacitive reactive power. Leading power factor operation is there. Now since current is leading the voltage, there will be a drop across this line reactance, and it will be a negative voltage drop. For lagging current, it is positive voltage drop. As you can see, for leading current, it will be a negative voltage drop. So it will not be in this direction. It will be in the opposite direction like this. It will be minus Ji into X. So therefore, what is this voltage? This is the sending end voltage. So therefore, your sending end voltage is receiving end voltage minus this drop. Or in other words, your receiving end voltage is sending end voltage plus this drop. Now this is a negative voltage drop. So therefore, we can very clearly see now that sending end voltage is less than receiving end voltage, or in other words, receiving end voltage is greater than sending end voltage. That is what happens in a transmission system. If transmission system has this capacitive reactive power, if it is operating at leading power factor, then receiving end voltage is higher than sending end voltage, right? So that is about this. And one more point is that again I will write that sending end reactive power Qs is equal to Vs square minus Vs Vr by X. Just few moments back we have derived this equation, and reactive power at the receiving end is Vs Vr minus Vr square by X. What is the difference between these two reactive powers? See, this is your sending end and this is your receiving end. Here sending end voltage is this, receiving end voltage is this. There is a reactive power at sending end, there is a reactive power at receiving end. Now if all the reactive power goes to the load, then in that case sending end reactive power minus receiving end reactive power will be 0, because all the reactive power is absorbed by the load. Let us see whether it is 0 or not. So Qs minus Qr is equal to, Qs is this, Vs square minus Vs Vr minus Qr. Qr has this again, minus Vs Vr. Then minus into minus is plus Vr square by X. So Qs minus Qr is equal to Vs square plus Vr square minus Vs Vr minus Vs Vr is 2 Vs Vr. If I write divided by X square, and if I multiply it by X, because X and square goes, it is again X. So therefore I can write Qs minus Qr is equal to, what is Vs square plus Vr square minus 2 Vs Vr? It is Vs minus Vr whole square. So this is Vs minus Vr divided by X whole square into X, this X. So you expand this, it is Vs square plus Vr square minus 2 Vs Vr divided by X square. And we already know what is Vs minus Vr by X. Vs minus Vr by X is nothing but current. Current is this voltage minus this voltage divided by reactance. So it is Vs minus Vr by X is current, and it is square. So I square X. So therefore the difference between sending end reactive power and receiving end reactive power is not 0, it is I square X. That means that the reactive power generated at the sending end, the reactive power generated at the receiving end, most of this reactive power is absorbed by the load. It flows over the transmission line and it is absorbed ultimately by the load. But the difference between the two reactive powers is absorbed by the line reactance. So there are two types of reactive powers on any AC system. One is the reactive power demanded by the load, and another is the reactive power due to the line reactances, due to the system reactances. Transmission line has certain reactance, inductive reactance, Jx, and this inductive reactance also absorbs some small amount of reactive power, and that reactive power is given by this equation, Qs minus Qr, and it comes out to be equal to I square x. It is called reactive power loss. So therefore, reactive power loss is equal to Qs minus Qr. It is equal to I square x. Just like active power loss is I square r, similarly reactive power loss is I square x. That means in an AC transmission system, in an AC transmission network, or in an AC power system, apart from reactive power demanded by the load, which is generated at sending end and receiving end, there is reactive power loss in the line reactance also. So you have to understand the difference between reactive power demanded and reactive power loss. The reactive power is the reactive power actually which is demanded by the load and which is generated and then absorbed by the load. And the reactive power loss is the reactive power because of the line reactance, transmission line reactance. So this is the reactive power loss. In a similar way, if you say active power, some active power PS will be generated at this bus, and some reactive power will be generated at this bus. And this active power plus this active power will be active power consumed by the load. And then there will be some active power loss also. I mean, this line may have some resistance also, and that active power loss is given by I square R. We already know that there is active power loss, which is also called copper loss, because of resistance, line resistance, which is given by I square R. Most of the active power, PS and PR, it is absorbed by the load, it is consumed by the load, but there is a small amount of active power loss, I square R loss. Similarly, the reactive power Qs and Qr, most of it is absorbed by the load, but there is a small reactive power loss, I square x. So just analogous to active power loss, which is given by I square R, we have reactive power loss, I square x, also in AC transmission system. I hope this is clear to you. So this was case A. Let us now consider case B. In case A, we have assumed delta equal to 0 degree. Now in case B, we will not assume delta 0. Delta is not equal to 0 degree, and we will also assume that Vs, sending end voltage, is equal to receiving end voltage, and it is equal to V. Now what is the sending end power? If you remember, sending end power, just few moments back we have derived this equation. This is Vs, Vr by x sine delta, and this is equal to receiving end power also, or I should write like this: sending end power is same as receiving end power. It is Vs Vr by x sine delta, and sending end reactive power is given by Vs square. Sending end reactive power is given by Vs square minus Vs Vr by x, and receiving end reactive power is given by Vs Vr minus Vr square by x, right? So for Vs equal to Vr equal to V. Now delta is not equal to 0. There is certain transmission angle or power angle, which is the phase angle between sending end voltage and receiving end voltage. Remember, this is always there. You cannot have delta equal to 0 for transfer of power over the transmission line. Delta has to be there. Okay. Now now assumption is that sending end and receiving end voltages are same. Vs is equal to Vr is equal to V. Substitute here. So therefore, power at the sending end, active power at sending end, is same as active power at receiving end. Vs is V, Vr is also V, V into V is V square. So it is V square by x sine delta. This is the same equation which we have derived in the previous class. P equal to V square by x sine delta. And what about Qs? Qs is equal to Vs is V, so it is V square, minus Vs is V, Vr is also V. So minus, this is here cos delta also. Similarly here, this is Vs, Vr, cos delta. I'm sorry, I have forgotten this cos delta. So Vs is equal to V, Vr is equal to V, so it is V square cos delta by X. So Qs is equal to, if you take V square out, V square by X, what we get inside is 1 minus cos delta, right? Similarly, if you see reactive power at receiving end, the Vs, Vr cos delta, Vs is V, Vr is also V, V into V is V square. So V square cos delta minus Vr is equal to V, so V square by X. So Qr is also equal to, if you take V square by X common, you will get cos delta minus 1. So these are the equations for sending end power, reactive power at sending end and reactive power at receiving end for Vs equal to Vr equal to V, right? Or we can also write Qs, sending end reactive power, is equal to minus Qr, and that is equal to V square by X into 1 minus cos delta. Okay, so Qs is this, Qr is this, or I can write Qs equal to minus Qr, which is V square by X, 1 minus cos delta, and if you see, it is half of I square X. It is half of the I square X, right? So therefore Qs is equal to Qr is equal to half, Qs is equal to minus Qr is equal to half of I square X. What does this mean? This means there is no reactive power flow. There is no reactive power flowing from one end to another, from one end to the other. Rather, let me first write, then I will explain. Rather, each end supplies half of the reactive power consumed by line reactance. Half of the reactive power consumed by X, that is half of reactive power loss. Half of the reactive power loss. Reactive power loss. I mean, this is your two machine model of the system. This is sending end voltage. This is receiving end voltage. This is line reactance. For delta greater than 0 degree, there is, delta is not 0, there is some delta. So therefore, there will be flow of power. It may be from sending end to receiving end or receiving end to sending end. Okay. And if delta is greater than 0, then Vs will lead Vr and power will flow from sending end to receiving end. And if delta is less than 0, then Vr will lead Vs and power will flow, active power will flow from receiving end to sending end. We will try to understand that with the help of Phasor diagram in a moment's time. Hold on. Now, you can see what about the reactive power? If this voltage is same as V, this voltage is also same V. You must always remember that reactive power always flows from higher voltage to lower voltage. If sending end voltage is higher than receiving end voltage, then there will be flow of reactive power from sending end to receiving end. On the other hand, if receiving end voltage is greater than sending end voltage, reactive power will flow in this direction. But in this case, the sending end and receiving end voltages are same. We have assumed that Vs is equal to Vr is equal to V. So therefore, reactive power will neither flow from sending end to receiving end, or nor will it flow from receiving end to sending end. That's what I have written here. There is no reactive power flowing from one end to the other. Rather, what will happen? That means there is no reactive power which is fed to the load, but there is reactive power consumed by or absorbed by line reactance. There will be reactive power loss. There will be no reactive power demanded, which will go to the load because the two voltages are equal. But there will be always reactive power loss. Whenever current flows through this line reactance, that results in reactive power loss I square X, we already know. And therefore, half of this reactive power loss, 1 by 2 I square X, it will come from sending end, and half of the reactive power loss here will come from the receiving end. That's what I have written here. Rather, each end supplies half of the reactive power consumed by load. That's half of the reactive power loss. There is no reactive power flowing from one end to another end or though no reactive power supplied to the load, because the two voltages are equal, which is an ideal case, which is not a practical case, remember it. But there is, because current is flowing, active power is flowing over the system, so therefore reactive power loss will be there, and each end will supply half of the reactive power loss, 1 by 2 I square x. So you have to understand this. And for delta greater than 0 degree, if delta is greater than 0 degree, I mean if this is your receiving end voltage and this is the current, then this is JIX, then this is the sending end voltage. Now you can see sending end voltage leads receiving end voltage. Since it leads receiving end voltage, power will always flow from sending end to receiving end. If the situation is like this, I mean VR and current is JIX, this is, I mean this may be VS, this is VR, this is delta, this is phi, here also this is phi. Here you can see receiving end voltage leads sending end voltage, VR leads VS, and therefore power will flow from receiving end to sending end. So for delta greater than 0 degree, power will flow from sending end to receiving end, and for delta less than 0 degree, power will flow from receiving end to sending end. Okay, so whatever we have discussed till now, we can generalize it. So I will write here generalized case. For generalized case, receiving and reactive power is Vs Vr by x sine delta plus j times Vs Vr cos delta minus Vr square by x. I have already derived it in the beginning of this lecture. So from this, active power PR will be equal to Vs Vr by x sine delta, and reactive power at the receiving end will be this part, imaginary part, that is Vs Vr cos delta minus Vr square by x. Okay, similarly we also know that active power at sending end will be same equation, Vs Vr by x sine delta, and reactive power at sending end will be given by Vs square minus Vs Vr cos delta by x. We have already derived these equations in the beginning of this class. And the difference between the two reactive powers, that's the reactive power at sending end minus reactive power at receiving end, is nothing but reactive power loss, and that is given by Vs minus Vr by x whole square into x. And just few moments that we have derived this equation also. Vs minus Vr by x is I, so this is I square x, and this is nothing but Q loss. Q loss means reactive power loss. Okay, so this is the reactive power loss without line resistance. In all this analysis, we have not taken transmission line resistance into account. Now, if transmission line resistance is also taken into account, so with line resistance, or if we take line resistance also into account, let us say line resistance is R, the reactive power loss is given by following equation. Reactive power loss is Q loss equal to, it is given by this equation, which is I square x, same, but in terms of active and reactive powers and line reactances, etc., it is given by x into PR square plus QR square by VR square. And similarly, active power loss, which is also called copper loss. Active power loss, it is given by following equation, P loss. It is given by I square R. We already know this is the copper loss. And it is given by line resistance R times PR square plus QR square by VR square. So therefore, one very important thing you have to remember that generally the active power flowing over transmission line, let us assume it is constant depending upon the load, but load reactive power may change depending upon the load power factor. So, during a particular time of the day when most of the industrial load is switched on, the power factor may be very poor, power factor may deteriorate, and reactive power demand may increase. In that case, when reactive power demand increases, that increases both active power loss, copper loss, as well as reactive power loss. Because if this QR component is increasing, you can see I increases in both the cases. I square X, which is reactive power loss, and I square R, active power loss, it increases, and it is clear from these equations also. And during other part of the day, when say in the evening late or late night, when most of the industrial load is off, QR decreases. Let us assume that hypothetically, let's assume that active power is same, it does not change. But since reactive power decreases, power factor improves when most of the industrial load is on, reactive power decreases, so QR component decreases, so active power loss as well as reactive power loss decreases. Both losses decrease. Okay, so this is the generalized case. Let us summarize what we have learned in today's lecture. I will give a summary of today's lecture. Summary is like this. Number one, the power transfer. When I say power transfer, it means active power transfer. The power transfer is controlled by two parameters, by line reactance control, and delta control, that is transmission angle control. Because P is equal to V square by X sine delta, voltage is generally constant, or it may be Vs into Vr by X sine delta. So if you are able to change delta, if you are able to change line reactance, you can control the active power flow over the transmission line. This is what FACTS technology does. With the help of FACTS technology, you basically change this line reactance, or you control the transmission angle, and you are able to control the power flow over the line. So power transfer is controlled by these two parameters: transmission angle delta and line reactance X. This is one first very important point that you must remember on the tip of your tongues. Then second is that for transmission angle delta greater than 0, which means that sending end voltage is leading the receiving end voltage, Vs leading Vr. P flows from sending end to receiving end. SE means sending end to receiving end. And for delta less than 0 degree, which means Vr is leading Vs. The active power flows from receiving end to sending end. Receiving end to sending end. I mean, if delta is greater than 0 degree, that means sending end voltage is leading receiving end voltage, which I have explained few moments back with the help of a Phasor diagram. Power flows from sending end to receiving end. But if delta is less than 0 degree, that means receiving end voltage is leading sending end voltage. Power may flow from receiving end to sending end. Remember this thing. Third point is that reactive power transfer is controlled by voltage control. Reactive power transfer is voltage controlled. I mean, if you are able to control the voltage by changing the voltage levels at receiving end and sending end, the reactive power flow can be controlled. Active power flow can be controlled by delta and X, which you have written somewhere here. Yeah, line reactance and delta, but reactive power flow can be controlled by voltage control. That is point number 3. Point number 4 is reactive power generally flows from high voltage side to low voltage side. Reactive power generally flows from high voltage end to low voltage end. What does that mean? That means that is, if sending end voltage is greater than receiving end voltage. I mean, sending end voltage is higher than receiving end voltage, then reactive power will flow from sending end to receiving end. So Q flows from sending end to receiving end. On the contrary, if receiving end voltage is greater than sending end voltage, then in that case the reactive power will flow, or Q flows from receiving end to sending end. This is another very important point. Fifth point is that for lagging power factor currents, receiving end voltage is less than sending end voltage, and for leading power factor currents, current receiving end voltage is greater than sending end voltage. I have explained it few moments back with the help of phasor diagrams. We have taken two different situations where when QS and QR was assumed, both were assumed positive reactive power. Positive reactive power means lagging power factor currents, which means reactive power is demanded by the load, is absorbed by the load. In that case, the voltage drop across the line reactance JIX, that subtracts from sending end voltage, and in that case receiving end voltage is less than sending end voltage. But if there is leading power factor current flowing over the transmission line, okay, that means if reactive power is negative, which means leading power factor current is there over the line, then the reactive voltage drop JIX becomes negative. It adds to the receiving end voltage and it makes receiving end voltage greater than sending end voltage. This is another observation. Fifth. Sixth is large reactive power can't be transmitted over long transmission lines, as it requires large voltage gradient. I mean, just few moments back you have seen that when reactive power flows over the line, generally it is lagging reactive power, it causes voltage drop. The receiving end voltage is less than sending end voltage always. And if you are transmitting a huge amount of reactive power over a transmission line, long transmission line, then the receiving end voltage will be much less than sending end voltage. That's what I am writing. Then it may not be possible for us to transmit huge amounts of reactive power over long transmission lines, because it will result in very poor voltage regulation. It requires large voltage gradient. There will be a very high reactive voltage drop over the line. Okay, so in that case we generally use compensators, series reactive power compensators or shunt reactive power compensators, like we may use TCSC, TSSC, SSSC, or STATCOM, or SVC, etc. We will study that in future lectures. Finally, if reactive power transferred increases, that is, if QR or Q increases, both active power loss, P loss, and reactive power loss, Q loss, increase. Which affects the efficiency of transmission, of power, or which affects the efficiency of transmission and causes poor voltage regulation. Try to understand this point. For same active power, transfer, for same active power demand, if reactive power changes, I mean, because I told you that depending upon the timing of the day, sometimes industrial load increases, sometimes industrial load decreases. the rise in industrial load means more deterioration of power factor, that means more reactive power transfer. So if reactive power transferred increases, then you have seen from one of the equations just few moments back, both active power loss and reactive power loss increase. And this active power loss and reactive power loss affects the efficiency of transmission, because when for example I square R is more there, the efficiency of transmission decreases. And this reactive power loss as well as active power loss, especially reactive power loss, it causes large reactive voltage drop, and that causes poor voltage regulation of the system. So these are some of the very important points which we have learned in today's lecture. In today's lecture, we try to develop some mathematical equations for, we have taken the two-machine model of a transmission system, and we developed the mathematical expression for apparent power transferred at the receiving end and apparent power at the sending end, and thereby we got the equations for active power and reactive powers both at sending end and receiving end. Then we took two different cases. In first case, we assumed delta equal to 0 degree, and we found that for delta equal to 0 degree, there is no power flow, active power flow from sending end to receiving end or vice versa. No power flows, active power actually flows, because transmission angle is 0 degree, but reactive power may flow. Okay, there may be reactive power flow from sending end to receiving end or vice versa, depending upon the voltage at the sending end and at the receiving end, and then that also results in reactive power loss, and that reactive power loss is because of the line reactance, and that is given by I square X. And this reactive power loss is similar to active power loss or copper loss, I square R. Therefore, whenever we calculate the reactive power which is to be generated by a compensator, we have to take care of reactive power demanded by the load and reactive power loss. Or whenever a generating station supplies, in addition to active power, it supplies reactive power also. In order to supply a certain amount of reactive power demanded by the load, the actual reactive power to be generated by the generating station must be more than the reactive power demanded by the load, because in addition to supplying reactive power demand of the load, it has to supply the reactive power loss, which is due to the line reactance, and which is also given by I square X. And in the second case, we found that if delta is not equal to 0 degree, but sending end and receiving end voltages are equal, then in that case, of course, there is the flow of active power as demanded by the load, but there is no reactive power flowing from sending end to receiving end or vice versa. However, in order to fulfill the reactive power loss due to the line reactance, half of the reactive power flows from both ends, from sending end as well as receiving end, to supply the reactive power loss due to the line reactance, that is I square X. And then we developed a generalized equation for generalized equations for active power flow, reactive power flow, and these are, then we made some very important observations. The first observation was that the power transfer is influenced by line reactance and transmission angle or power angle delta. And second observation was that if delta is greater than 0 degree, that means sending end voltage leads the receiving end voltage, there is the flow of power from sending end to receiving end. And for delta less than 0 degree, that means receiving end voltage leading sending end voltage, power flows from receiving end to sending end. We also found that reactive power transfer is controlled by the voltage control. Another observation was that reactive power generally flows from higher voltage side to lower voltage side. So therefore, if sending end voltage is greater than receiving end voltage, reactive power will flow from sending end to receiving end. And if receiving end voltage is greater than sending end voltage, then reactive power will flow from receiving end to sending end. And we also found that for lagging power factor current over the transmission line, there is drop in the receiving end voltage, and for leading power factor current over the transmission line, there is a rise in the receiving end voltage, that is, receiving end voltage becomes greater than sending end voltage. We also found that this large reactive power cannot be transmitted over a long transmission line because it requires large voltage gradient. And finally, if the reactive power transferred over the line increases because of the reactive power demand of the load increasing, both active power loss as well as reactive power loss increases, which decreases the efficiency of transmission and also increases the voltage regulation or causes poor voltage regulation of the system. So these are some very important observations for an uncompensated power transmission line. In our future lectures, we will now try to study why is there need for compensation, and what are different types of compensators, how they work, and how they try to compensate the uncompensated transmission lines and improve their performance. With this, I will end my today's lecture. I advise all of you to go through this lecture, and in case of any queries, please feel free to ask me, put your queries on the group. I wish all the best to all of you. Thank you.